Yeah. Same process. Exact same thing.
Yeah, so I put up in class there and I downloaded lecture 11 and it's the slides from PlanFest. And I'm far, so if I get here and run back.
Yeah.
Plus, I'm like, I already had to cancel this morning's class. It's just I cannot do that. So Canvas has, so I had last year's slides.
Nice.
I just had to go with that.
That's so funny.
You didn't even notice.
No, I need to know because I had updated the presentation for like an hour. I usually update the examples every year.
Yeah.
And just had to wait it. Scary.
I think there's something must have been like wrong with the computer system. In aquatic biology, the professor was also having issues.
Yeah, but
Like
I
something
think
was
the
weird.
problem is because I have separate folders, but both of them were lecture 11 with the same date. So when I uploaded it to Canvas, I must have selected the wrong file folder, and the file name was correct. But
Yeah.
it was the wrong folder.
So funny.
I think it probably closed at 10:15. You want to finish?
Yeah. Yeah, I was so confused by it. It was like positive.
Okay. Good. Okay. Okay. So let's talk about that. So whenever we look at a plant cell, there's many things being transported in and out and all of that. So one of the things here is that, of course, the idea is not, I don't know any of these things by heart, but the idea of this part is that if you get to see a picture like this, because we understand the requirements for the different types of, either channels, transport through channels, or transport through importers or pumps, then we can predict or kind of have an idea of the concentration of ions on one side relative to the inside if we get to see one of these pictures. So I don't know how likely it is that you can actually see it, but if I show you this picture, this part of the picture, and I said, how is the concentration of calcium in the extracellular space and the cytoplasm and the vacuum, like relative, based on that picture? What can you say to that?
Probably lower than outside of the cell.
Yes, so you see calcium by all of these channels is entering through channels, so you know calcium has to be higher outside than inside, right? And also inside of the vacuole, there are channels transporting calcium from the vacuole outside. So you know the relative concentration of calcium has to be higher in the vacuole relative to the cytoplasm and higher in the extracellular space relative to the cytoplasm. So again, it's not memorizing any of these. So just kind of understanding what that tells us about the concentration. So when we talk about membrane transport proteins, we have channels, carriers, and pumps. Again, this is just review. I just want to make sure we quickly go through this to make sure everybody's clear on this. So how is transport across channels regulated, and is this passive or active or it depends? How do you regulate movement in channels?
Channels are like the diffusion, so it'd be passive, just going from
Yes.
high to low concentration.
So it would be passive, you need a higher concentration on one side, versus the other, and channels are usually regulated, so they're open or closed, right? So they can be voltage gated, mechano gated, or light gated. So open or closed, but always passive, so driven by concentration. What does this tell you about the concentration of glucose?
Figure B would have less of a glucose concentration inside, whereas in figure A, they're going against the gradient, so it'd be higher in figure A.
Yeah, so in facilitated diffusion, this is a transporter, so glucose doesn't move through channels, it's transporters. But then it's telling you facilitated diffusion always goes in diffusion, so higher to lower. So whatever it is, glucose has to be higher here versus inside. Secondary active transport is still, a type of transporter, but in this case, while it's not primary active transport, like pumps, like the sodium potassium pump, it is going to require some energy, but it's not the same type of energy, so not directly some ATP, but it's going against the concentration rate. So you can assume that if glucose is using secondary active transport, then glucose is going to be higher here than here because it's going against the concentration rate. So it's not using a transporter, it's using secondary active transport. So it's higher to lower and then going against. So I think we kind of read this already. So carrier or transporter proteins are going to be diffusion. Okay, if we're talking about the facilitated diffusion. And then when we talk about transporter proteins, they can also be secondary active transport. So in secondary active transport, hopefully you remember, but what happens is that some kind of additional protein pump usually will use some energy to drive some concentration. So here, for example, you can see that something else is accumulating this gradient of hydrogen here, so you have higher to lower hydrogen, and then you can bring S against the concentration gradient because you're taking advantage of this gradient that has been created by the hydrogen on the other side. So you actually need one secondary active transport only needs one type of transporter. It relies on another transporter creating a gradient that is favorable for the secondary active transporter to bring things down the concentration gradient. Is that clear? Okay. And then one of the things is in secondary active transport, we have C-porters and anti-porters. What is the difference between C-porter and anti-porter? Yes.
Same for going the same direction.
Yes. So in C-porters, you can see you're bringing two things in, right? Same direction. Anti-porter, you're getting, hydrogen in, and then the other one, the opposite direction. And then active transport, the traditional sodium potassium pump, one of the pumps you've always heard about, you use ATP to pump things against the concentration gradient. You need ATP to do that. here, let me see it here. But it's fine, I think you can see it here, sort of. So would that be an electrogenic, electroneutral, or electrogenic pump?
Electrogen.
Yes, because it's not neutral, right? Remember, you're creating, there's a difference in the charge that you're generating. So what happens is when you think of neutral pump, is like when you acidify the stomach and you have the hydrogen potassium pump, that one goes in, one goes out. That's electroneutral, right? The electrogenic would be like the sodium potassium pump, that you have 3 out, 2 in. So by getting 3 out and 2 in, you're making the interior slightly more negative because you're getting 3 positive charges out versus just 2 in. Okay, so that is very important. Also, super important, plants do not have sodium potassium pump. Okay? They don't have sodium potassium pump. So how do they create that interior more negative that we briefly talked about with this kind of pump? So basically what you see is the hydrogen ATPase uses energy to basically pump hydrogens outside of the cell and hydrogens inside of the vacuum. And in turn, you probably want to learn tonoplast. Tonoplast is the official plant name of the vacuole, the plant vacuole. The membrane of the vacuole is called tonoplast. So you have this one here pumping hydrogens, this one here pumping hydrogens. So what does that tell you about the pH of the apoplast and the vacuole relative to the cytoplasm? Yes.
They'd be more acidic.
Yeah, so you can see here basically it's pumping against the gradient, so you're accumulating a lot of hydrogen, you're lowering the pH in the apoplast, and you're lowering the pH in the vacuum relative to the cytoplasm. So the cytoplasm is going to stay close to 6.7, 6.8, but the outside and the vacuole need to have that gradient. Now, if you look at this image that is here, for example, you need that gradient, you need that excess of hydrogen ions outside, because plants rely on that to bring many things in and to get things out. We're going to talk about this later on, I believe, on Friday's class. But for example, this is key. You know, salinity and accumulation of sodium in plant cells can be a problem. So plants can actually use some of these gradients to pump some of the sodium out. So plants rely on those gradients to bring things in and out, and similar in the vacuum. They need that electrochemical gradient. And so because of that, that generates, you're pumping things out here. So that generates a gradient that if you measure the outside versus the inside of the cell, that gives you the membrane potential that is more negative on the inside relative to the outside. And again, how do you do that? You probably remember these or have seen these more related to neurons. You take this voltmeter and then you have, one of the electrodes outside, the other one on the inside of the cell, and then the inside is going to be negative, so the voltage difference, there's going to be a voltage there. And the typical plant cell is ranges. So, similar to what you've learned, animal cells is going to be more negative on the cytoplasm. And so that brings us to the Nernst equation. So the Nernst equation can be used to determine if an ion is at equilibrium across it. Okay. So we know there is this voltage, right? And I want you to start thinking of equilibrium. Remember, equilibrium doesn't necessarily mean that there is 6 and 6, or 5 and 5. Equilibrium, it depends on the concentration of the ion. Also, the ions are charged, but also on these voltage shifts. So the Nernst equation basically tells you, is the ion concentration at equilibrium across the membrane? And so kind of the general idea is that the ion would be at equilibrium, let's say sodium would be at equilibrium, again, outside versus inside, and that will depend a lot because it's charged on the actual membrane potential of the plant cell at that time. And we're going to see how that happens. So we're going to learn, or we're going to revisit two terms. So the Nernst potential, that is the equilibrium potential, is En. That's the formula that you worked on at home. And then the actual membrane potential, and I will tell you what that means. This is something that you measure. So this value, you would actually get it like this. So you get this voltmeter and then you measure it and you determine, okay. So I determined that these cells have a membrane potential of minus 110. Okay. And then I figured out that the concentration of these three ions, sodium, chloride, and potassium, is exactly this much. So I determined the membrane potential. These ions is exactly the concentration inside versus outside. Are they at equilibrium? And then we'll see what that means in terms of transporting the ions in and out. So the first thing is, this is what you did. So again, assume you calculated or you determined the concentration inside of the cell versus outside of the cell. Here we're calculating the Nernst potential for an ion, how many inside the cell. So what is the Nernst potential for sodium, chloride, and potassium? From now.
Sodium is negative 53.4, chloride is like 49, 50, and then potassium is negative 110.
Potassium is what? Sorry?
Negative 110.
Yes. So, the equilibrium potential gives you something similar to that, right? So, okay. So this basically tells you, because this was here. So once you calculate if the equilibrium potential is different from the actual membrane potential, it tells you it's not at equilibrium, right? So it tells us that basically these two are not at equilibrium. This is not 110, but this one is. So from here, we have two ions not at equilibrium, one of them at equilibrium. So let's start with AC. What does that mean for potassium? That means that potassium can basically diffuse in and out of the cell at a similar rate, depending on what the plant needs, because it is at equilibrium for this specific one. Now, what does that mean for sodium and chloride? We know they are not at equilibrium. There has to be a gradient. So how is this gradient? Because remember, that's going to tell you something important. What does this tell us about the transport of sodium and chloride into the cell? So, let's recap. If the Nernst potential is not the same as the membrane potential, then there is a gradient. It's not at equilibrium, there is a gradient. That means that if you have just continue our gradient story, if you have a gradient, what does that tell you? In some direction, it is going against the gradient. That's going to be up. Down the gradient is going to be diffusion. So, is the gradient, is this in and this out? Or is this in and this out? How is this gradient? That will tell you, okay, if this is the gradient for sodium that is higher inside of the cell than outside of the cell, then you know it's going into the cell by active transfer. But if the gradient for sodium is the opposite, it's lower on the inside, then it's basically, it's lower on the inside, then you're basically going, it's lower on the inside, then you're going out by active transfer. Okay, so let's see how this goes. So how do you figure this out? You can now use the actual membrane potential in the Nernst equation to predict the internal concentration at equilibrium. So remember this, you have the actual values of sodium, let's start with sodium in and out, and you calculated this. which is the Nernst equilibrium, and it's different. Okay, so now you're asking, well, because the actual membrane potential is different. So if when I use the actual membrane potential, what should be the ratio of solute in and out at equilibrium? And then comparing that to my actual values, I can see how the gradient is. And let me explain that step by step. So the first thing you're going to be doing is replacing this Nernst potential by the actual EM value. Okay? And then you're going to solve the rest of the equation. Now, another important thing is how are we going to solve? So, okay, we have this figured out, right? So, but we clearly have to solve the rest. So, how are you going to be doing that? So, first of all, similar to what I tried to do here, because we know we are not at equilibrium, you have two options. If the actual concentration of your ion inside of the cell is higher than if it was at equilibrium, if it's higher than at equilibrium, then you know you have this gradient. At equilibrium would be something if your actual value is higher, you have this gradient, and then it tells you it's going in by that and leaving by that. That's one option. The other option is that the actual concentration that you get is lower than if it was at equilibrium, and then this is how your gradient will look like, right? And so basically, you're going in by passive transport and leaving by that. So that's what we're going to be figuring out. Is it higher than if it was at equilibrium, or is it lower than if it was at equilibrium? So how are we going to solve for that? So let's start with solute. It's the same equation, right? We're replacing this by the actual membrane potential, right? And then, because we have to maintain one of the other variables stable and the other, we can only change one to solve for this equation, because we're figuring out what the concentration inside is at equilibrium, then we leave the outside if we use the actual one and calculate. When I have this membrane potential and the outside concentration is this, what is the inside concentration of this? Okay, so I want you to solve it. Also, if you're having trouble with the logarithm, then your worksheet is how to help you solve that logarithm. I don't know if you catch this from the book, but all of this for a monovalent ion is 59. All of this is 15. If it's chloride -1, that is -1, it will be -2. So if you have a monovalent, it's going to be 15. Just keep in mind if you have something that is, I don't know, magnesium or something that is +2, then that's going to be. Let me see if I have it. Actually has it.
I didn't have an active one. I don't really for him. I'll get value. So I'm using that.
Yeah.
You can take the bar. Where is it? Power of 10? Like the 10 to the. No. This is your. It's
No.
Use the log. You're solving for the concentration. So instead of using that A value, you're like solving for that.
So all you have to do for now is solve for this. We'll figure out the gradient and the equilibrium later on. For now, let's just solve for this side.
Still working on it.
So hopefully looks something similar to this. I just have to do it step by step. So you did it all in a calculator. You don't have to write it. So what did you get for the concentration of sodium on the inside? Yes.
50 normally?
50. Well, it's a little bit higher. I got this, so that's why I kind of worked it step by step. So this is, I don't know if you solve it like that. That's how it solved. Put it all step by step. If you got the similar value, you did it on your calculator all at once, great. I cannot do it all at once. So get a value of 72, 74 again, plus or minus 2, it's in the range. So this is telling me that with that actual membrane potential, let me give you a minute. Like this. Was it similar or?
Yeah, I just
Okay.
rounded. I think I just punched something in.
Okay,
The same
good. Okay, good. Okay, so roughly what this tells us is that our table, I don't have the table anymore, but I think our table said that the inside concentration, that the actual, what we had in this cell that we measured, the outside was 1, the inside was 8, and the membrane potential was minus 110. And we said, okay, this is not an equilibrium. So now we said, okay, if we have the outside at 1 and minus 110, what would be an equilibrium, right? You calculate the inside instead of 8. What would be the concentration? What does the solute concentration need to be on the inside for this to be an equilibrium? If it's not 8, then what is it? That's basically what we're asking. Okay? And we got 72. So let's think about it. So we have a cell, and we said outside is 1 and inside is 8 millimolar. This is the actual thing. If this was an equilibrium with the actual membrane potential, it would be 1 and 72, right? So, is the actual concentration higher or lower than if it was an equilibrium? Is the actual concentration higher or lower than if it was an equilibrium? Is 72 higher or lower than 8? Higher, right? Higher. So, or 8 lower than 7. Basically, the actual concentration is higher. So what does that mean? That because the actual concentration is basically, what do I? I think I have this. So what was the inside? Was it 8? Yes, it was 8.
Because the observed was 8.
Yeah, sorry. Can you borrow your worksheet? Yeah, thank you. So that concentration, oh yeah, it was correct. That is 1. So let's say now we have
I think that's just this.
so basically what we have is if this was an equilibrium, we would expect this to be 72, but it's not 72, it's 8, right? Because 8 is lower than 72, yeah, basically 8, depending on what you do it. You should have 72, but you have 8. Because this is lower, then you have a gradient, right? It's much lower than you could expect if it was an equilibrium. You have 8 instead of 72. That means that your gradient basically looks like this. Right? If it was an equilibrium, you would have 72, but you actually have lower, you have 8. So it's much lower inside than if it was an equilibrium. Therefore, your gradient looks like this. Does that make sense? You were expecting, I'm trying to draw in this equilibrium, but drawing an equilibrium when it's not. So if this was an equilibrium, it would be, I don't know how to do this, because 1 and 72 can't really get at equilibrium. But it's not like this. This is actually much lower than 70. So this is your actual grade that you have in the cell that you have. Because that's the gradient that you have. I will represent it like this. So basically, what does that tell you about sodium? How is sodium entering the cell? Passive or active transport? Into the cell. Passive transport, right? If this is your gradient, then sodium is entering the cell by passive transport. How is it leaving the cell? By active transport against it. So in the current conditions in this plant cell, sodium, you have this gradient, is entering the cells passively and is actively being transported out of the cell. Okay? Now let's do chloride. Remember to change the charge in chloride is different from sodium.
Yeah, she said
Do you think that is good?
You know, I didn't drink any water today. I did make myself a smoothie like right before I left, so I thought that would like hydrate me a little bit. So good. Such a good smoothie. I'll show you what I'm enjoying. It gave me like a grave which we were gonna die on top of it. So we carry around a lot of water. Just like general flask. Oh yeah, it said drink it fresh, you know. It's nice. But I only do dishes. I want to drink it like straight up out of the little dishes as possible. Yeah. I don't follow like maybe so much that I pass on that actually see it. I do that too. It's good.
Yeah, so this one, so you have to solve for the C1. The C1. And remember, C outside is the same as C1. So you don't have to change that. All you really have to change is the symbol of the C. So, which is
this.
yes,
And then after that,
you divide this over this.
and then take the log.
Yes. And so, yeah, so
But
what
then,
did this
so
give you?
it was like 70. It was the same as that, 72.
No, because so the previous one was the power was so it was negative and now it's positive.
So is it gonna be like 20 something?
It's going to be
Fruit juice has got to
That's
water.
up to bed. I was like,
Yeah.
I felt like it did that.
yes. No, it's yes, 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 because now it's positive instead of yes.
Okay. To the one. So yeah. That point over to
Okay, so this time I want you to, if you have a value, now try to tell me how is fluoride, how does it grade? I want you to predict that consider groups and figure out how the gradient is, and tell me how chloride is entering the cell. Passive transport or active transport? And then we'll talk about how you decided that. Yeah.
Concentration inside. Lower.
So not it is not because your log was
And I got 0.01. But it's such a low minuscule.
but it tells you that
Yeah, that's
that if the system wasn't
that.
that is the concentration for a system. And that's not what you have, you have seven. Somehow to
Unless for some reason.
So it's high.
But yeah, so that's just gonna.
Alright, you going?
No, you guys can discuss it.
Do you want to help with the math? Or?
I'll be okay. I'm
I still like 0.6 conceptually about that. Algebra master, but once you know how to like. So literally, it's so algebra is so nice. Just like so straightforward. Like me, no concepts. That's like every step. Multiply by one. What? I guess I did it.
Wait, oh, recessive.
Yeah, I do it systematically.
So.
My mom, so I was like looking at my mom. So it's like real nice. It's like everything being like super like organized. We're doing that. So we're gonna see that guy. We're just like so.
So did everybody get a similar value to this one? Good. So in this case, the only, well, it changed, but the thing that's changing is that the chart, here instead of positive 59, you have a negative 59, and that just basically, changes, instead of trying to go minus 1.86. So you divide that, and so is, how is the actual concentration of chloride? Higher or lower than if it was at equilibrium? Yes, so at equilibrium, it would be 0.014, but you actually have 7. So now what you have is much higher than if you had this at equilibrium. That means that how is the gradient?
It's so standard.
Yes, it's basically what you have is 7 is higher, 0.14. So basically your inside concentration is much higher than if you had it at equilibrium. So now what you have is basically you have basically this gradient. So it is entering the cell by active transport and it's leaving the cell. Okay? That's how you will figure it out. Okay, was that clear? Good. So I will be uploading later today just another example for learns, potential problems so that you can practice on that for midterm. So and then it's going to be, a similar thing. So this is the concentration, this is your ion, how is this ion leaving or entering the cell? And so basically now you know that all you have to change, you know that the whole equation in this part is 59, then all you just basically have to modify it depending on the charge of the ion that you give. +2, -2, +1. Okay? Okay, that's it. So I will, please leave your assignments and I will see you ready? Right.
Clear out the underground and then put in solvent where
Were we supposed to answer these other questions throughout?
No, it's just this.
Alrighty, cool. Yep, I'm gonna take a picture.
See you. Good luck with that.